Okay, yes, Hannah. Let's start off with a question. Okay, let's go for the four-wheel drive or the two-wheel drive thing first. Then we go on to the one that you talk about. Okay. So we are okay with the idea that if it is front-wheel drive car, if the front wheel is the one applying the kick, then the friction over here is this way, and the friction over here because it's dragging is this way. Yeah, Ken. So what happened is that if you got a rolling ball, yeah, isn't a rolling ball this case over here? Agree or not? The back wheel is just rolling. It is not doing anything. So isn't this wheel the same as this wheel? There's nothing dragging it forward. It's just rolling. Okay. The thing is, it is this frictional force that enables it to roll. Yeah. So it is because of this frictional force that's why it rolls. Otherwise, if there's no frictional force, it will just slide. The fact that you see a ball rolling, it means that there must be friction that is backwards. And the fact that it rolls this direction, it means that the frictional force must be assisting the rolling. Yeah. If just hang on up, if the frictional force had been this way, then you actually stop rolling and then reverse its direction. Okay? Yeah. Okay, let's say for example, if it is done in vacuum, if this is done in vacuum, it will not slow down. If it is a perfectly hard surface, perfectly hard ball, no deformation and all, it will go on forever. Yeah, which is actually a very interesting thing if you think about this, that actually friction doesn't slow things down. Because you've been taught probably in year 3 and year 4 that friction always resists. Or probably a higher order thinking is that sometimes friction helps to move things forward. But there are cases where friction doesn't help things to move forward, neither does it slow things down. It just keeps on moving forward. Now, one question, is it possible for things to be perfectly hard and perfectly rigid? No. Everything deforms by a small amount, it's just that we cannot see. So over time, the deformation of the object will cause it to slow down. And there were a lot of interesting things that I brought across the last lesson. Remember I said that frictional force, when you start to move, I think one of you asked this question, when you start to move, the frictional force actually starts to decrease. Why is it so? Have you thought about this? I take it that the silence means that you're still thinking. Why? Then we need to go into the why is there friction? Why is there friction? In a hypothetical situation, if something is perfectly smooth, would there be friction? No. So do you agree that therefore we can deduce that frictional force is due to the undulations in the surface? Right? And the undulations create friction because of this. See, in the very scary case of having a surface that looks like this, and when you try to move this surface forward, do you agree that if this side will push against this side, and therefore this side will exert a force that is this way on the object? In fact, the different teeths will exert this force on the different surfaces, and the horizontal component of that force gives you the friction. Now, using this model, then this is scientific thinking, using this model of friction, then we apply this to when it's moving. Now, when you have interlocking surfaces, when it is stationary, do you agree that it locks deeper? Now, when it starts to move, what happens? It bounces off, correct? It doesn't go in as deep. And that's why the frictional force starts decreasing. Yeah? That's why the frictional force is lower than when it's stationary. It doesn't go in as deep because it's just bouncing off the surface. Understand? And the surface, if it is this one, if it is at the tip, can you see that the tip can bend more? Yeah, it is more flexible. So the horizontal component starts to decrease. As you bend, see, as you bend like this, versus when you go this way, the horizontal component is bigger for this case as compared to this case. The horizontal component of the resistive force, when it is not bent, when it's stationary like this, is going to be higher than the horizontal component over here. When it's moving over the top and bending the top of the jagged surfaces on the surface. So the decrease in the horizontal component of the frictional force causes the decrease in frictional force when things start to move. Yeah? How much does it decrease? Just hold your question. Remember your question now, because sometimes senior people like me, sometimes you raise your hand and forgot already. After 2 minutes, you'll forget. So remember your question. So the decrease, the amount of decrease will differ from surface to surface. Yeah? Well, it depends on how flexible the surface is and amongst other factors. Your question.
But I thought as speed increase? Like, for example, like air resistance will increase as speed increases.
That's a very interesting question. So does frictional force decrease or increase? Does the decrease, okay, say for example, when you go from this stationary to this, does across time and as you move the object, does the friction go this way or this way? That means does the frictional force change over speed? Technically, it shouldn't. But a lot of times, no, relax. But you see, I told my students 4 years back that frictional force doesn't depend on surface area. I also told my students that frictional force doesn't depend on time in contact with the surface. But one of my students in his IA, he researched on how frictional force changes with time, and he found that it actually changes with time. You put the two objects together for 5 seconds versus 10 seconds versus 1 minute, the frictional force actually starts to increase, and then it plateaus. Yes, correct. I said that frictional force doesn't change with area. Once the other students research on same mass, different area, changes. So by right, it should not change with speed. But if you can do an experiment, the difficulty of this experiment is that how do you control speed? Yeah, that's the difficult thing. How do you measure and control the speed? But if you can, I think you might, my take is that you might find, what do you think? Is it going to be a decreasing friction, constant friction, or increasing friction as you increase speed? Based on this model. Decreasing? Okay, someone said decrease. Anyone else say decrease?
Based on this model.
Based on this model, yeah. Decrease, right? Because the lesser it will go in. Yeah. I think it will decrease. But the challenge is, at what point of speed will this show that significant decrease and whether it decreases at all? But if it doesn't decrease, you should be happy as well because it proves that this model probably is incomplete. Yeah?
Then what is it that causes air resistance to increase?
Air resistance, there are two sources of air resistance. One is laminar, one is the shear force, one is the literally the banging. Yeah. As you go over here, as you go through air, you have air going through here. Yeah, so this one is like pulling the layers of air across. So you got different speeds. So it's like layers of air getting dragged across. That is one, and that one is actually proportional to V. But there's another one where if you go here, do you agree that the air molecules knock into that? Originally it's at 0 speed. This one is pushing the air, giving it KE. So this is the other component of air resistance. So there are two. And that one, as you would have suspected, this one is going to be more than this one. And this one is V squared. Yeah, this one is V squared, this one is V. Yeah. But if you can actually design an experiment that you can do, research how frictional force changes with speed, I think it's an awesomely interesting experiment that I personally would want to know more about. Yeah. No, I don't know whether you can find literature on this. Good and bad. Bad means that you don't have anything to rely on. Good means that you're trailblazing. Yeah, good means that you're trailblazing. If you do something that no literature kind of thing. Cool? So think about this. But please don't go into the area where you start investigating whether color affects friction. Come on. We know that it shouldn't. Yeah? Cool? Now, let's talk about numbers now. Remember I talked about this, did I talk about this F equals to mu n? Have I? I haven't now. Okay, good. So the frictional force, in fact, I would like you to always remember maximum frictional force is equals to this thing called coefficient of friction, and then multiplied by normal contact force. Let's start off with n first. Let's discuss about n. Tell me whether this statement is correct or wrong. Normal contact force is always equals to weight. Correct or wrong? Why? Can you, okay, incline, that's good. And then any other situations? Elevator, exactly. So normal contact force and weight, they are not exactly always equal, depending on situations. Inclined plane, elevator moving up, does it mean that n equals to w or n not equals to w? Okay, I'm gonna screw your mind a bit. When when the elevator is moving up and slowing down, is n bigger or lesser than w? When n is going up and slowing down. Oh no. How about when lift is going down and slowing down? When the lift is going down and slowing down versus the lift is going up and slowing down. Starting to get giddy already. Okay, we park this, we'll discuss this later, but we know now that n is not equal to w. That's why I want to drive home. Yeah? We'll talk about the lift later on. Can? Yeah, so what I want you to remember is n need not be equal to w. That's the key thing. So normal contact force equals times mu. Remember that just now we talked about stationary, so there is coefficient of static friction and coefficient of kinetic friction. Come on, need no explanation. This is when it's moving, this is when it's stationary. And this is going to be always bigger than the right hand side one. Cool? Now I'd like to unpack this a little bit further. Very important idea, and IB loves to test this, and we love to test this as well. Because as teachers, not that we enjoy seeing students make mistakes, but there are certain things that we want to drive home, conceptual errors, and this is one of them. Okay, listen carefully. F equals to mu n. So say for example, you found mu n to be 2 newtons. Yeah? Say, mu times n gives you 2 newtons. If I pull the object with 1 newton, what's the frictional force? 1 newton. It is not 2 newtons. If it is 2 newtons, you know how creepy it is, you know. You pull a bit, it goes backwards. It doesn't make sense, right? It's very creepy. Yeah, because some students will have this impression frictional force is always 2 newtons. No, please be careful. It is maximum frictional force. That means it's like a reserve of friction. The maximum I can challenge you is 2 newtons. So if it is 1 newton, it is 1 newton. If it is 2 newtons, it will be 2 newtons. Only when it goes to 2.1 newtons, then it cannot give any more. You'll stay at 2 newtons. Then the object will start to move. Yeah? And when it starts to move, the friction will suddenly drop down. So there'll be a jerk kind of thing. It is not smooth. Yeah? Because once it starts to move, the friction drops to probably 1.6. And then the acceleration will be higher. Okay? So if you actually track the acceleration, you'll find that with time, force, acceleration, it will start to move for a very short period of time, then it falls down to a lower value. This is the static part, and this is the kinetic part. Okay? The split seconds where it transits from static to kinetic. Cool?
Do things with more mass have like more friction?
Okay. More mass will result in more n, therefore results in more friction.
Okay, let's say something was like traveling like near the speed of light.
Oh, okay, here we go.
The mass is like
Okay. Okay, let's be very clear. What she's saying is light speed. Okay, for those of you, have you heard of E equals to mc square? Must have lah, must have E equals to mc square. So when something travels near light speed, okay, you must be careful to understand what does it mean by mass increases. Because when you accelerate anything near the speed of light, the energy goes up with this. The energy, not the mass, I must be very careful. Energy is equals to rest mass over square root of 1 minus v squared upon c squared. So what happens is that if you go near the speed of light, this is going to go infinite. It's going to rise really, really sharply and steeply. But because E equals to mc squared, it looks as though that mass is increasing because this is equals to m naught c squared. It's the rest mass when it's stationary. So it looks as though that the mass is increasing, but you have to be careful. It's actually due to energy, not mass. But the equivalent of energy is interpreted as an increase in mass. So it looks as though it gets heavier and heavier, but it should be interpreted, it gets more and more difficult to accelerate the electron or the particle. But it is not a change in the physical mass. Yeah, it is the energy that goes up exponentially. And we interpret the energy exponential increase in energy as an exponential increase in mass. Yeah, it gets more and more difficult to accelerate. So we see that, we feel that as an increase in mass. but it's not a real increase in mass. Yeah, can? Otherwise, Mr. Higgs will be very upset. Yeah. If you don't know what is Higgs, is a physicist, still alive, right? He's still alive. Higgs. He came out with this Higgs boson, the God's particle. Yeah, God's particle. Which, if you have the chance to go to the sun, you get to see. Rub salt on the wound. Okay, let me try. Let me try to find ways to bring you guys there. If I honestly, if I can bring you there, this year year 6 will be so sore about it. Yeah, they'll be so. This year 6 don't get to go. There were some changes. Yeah, but it's not because CERN don't want us. I've been enjoying very good relationship with the CERN officer there. It's some things happened along the way so yeah. And this year 6 cannot go. So if y'all can go, I think they'll be like, let me try. Yeah, Ken? I think the trip there, the 6 days there, I spent with 6 batches of students. One of the highlights in the whole ASP program.
Can you explain the Higgs field?
Okay. I think let's take it offline. Okay, it takes a lot to explain the fundamentals. But basically, if you want to know a little bit about that, allow me 2 minutes. Let me explain the concept of why particles come into the picture. Yeah? So let's take a look at plus and plus. Why is it that particles experience? It's the fundamental question of why is it that forces at a distance appear? Why is it that positive and positive repel? If you think about it, it's actually very interesting. 2 isolated particles, there's something happening between them. So what Richard Feynman came up with was, a very famous physicist, is that the interaction between these charges is due to the exchange of photons. So between them, a lot of virtual photons start popping up through. It's just like 2 people on a piece of ice. If you throw photons at each other, you throw bowling balls at each other, the 2 of you will start moving away from each other. Yeah. So the force from a spooky whatever we don't know what happens. Now the idea is that the force is actually transmitted by photons. That means the exchange of particles is due to, now how about attractive forces? That means attractive forces is due to these 2 particles sharing, like 2 persons holding on to the same particle. So the idea of a force gets converted into ideas of particles exchanging. Yeah. Again, so how? That leads on to this thing called uncertainty principle. Uncertainty principle says that. Uncertainty principle says this. Have you heard of this before? Yes. Uncertainty principle. You look uncertain. Basically, what this equation tells you, right? Do you agree that if this is small enough, this can become big enough? Yeah? That means that if this is big enough, remember E equals to mc squared? That is to say, on a time scale that is small enough, in femtosecond scale, say for example, you can have an uncertainty plus minus that is big enough for a particle with certain mass to pop out of existence, or energy to pop out of existence. So actually in the quantum world, right, even in absolute vacuum, a lot of particles are popping out and disappearing at the same time. So these particles are actually popping out in between these 2 charges. Particles are popping out and disappearing every time. Now when do these particles start to become real particle? When there are electromagnetic changes. That's why when you have electrons exciting or de-exciting, you have photons escaping out from this interaction. That means the photons were already there. That means it's hopping in and out between the protons and the electrons. It's just that during those changes, one of them get lost. That comes out. Yeah, lost to what we see lah. Like the emission spectrum of atoms. That's what we see. And so it's this model is what he understands. Richard Feynman came up with this thing called the Quantum Electrodynamics, which he came up with 2 other people, and the 3 of them shared the Nobel Prize because of this. Yeah, it's a very beautiful model. If you think carefully, gravitational force. We talk a bit about. Do you know what's the model for gravitational force now? Albert Einstein. It's a distortion of space-time, exactly. So he understood that as distortion of space-time. So Richard Feynman and his two other teammates understood electric force as a distortion, as a particles exchange. Yeah? If you think about magnetic force, have I told you that magnetic force doesn't exist? Yeah. I told you, right? Okay, yeah. So if you go deeper and deeper into certain things, a lot of times we say that we know. Higgs came up with Higgs boson because he asked, what gives particles mass? Coming back to your question, he understood mass as if you've got something moving in free space. When you move something through free space, its different particles will interact with these particles called Higgs bosons differently. The more this particle interacts with more particles around here called the Higgs boson, the more mass it experiences. The most famous example, the most popular example is someone going to a party and a celebrity going to a party. You have a lot of people crowding around that celebrity. Yeah, some of them will relate to JJ. So imagine JJ coming to a party, thousands of people will come to him. That will make him very difficult to move around. So that difficulty to move around, remember mass is the measure of reluctance of a particle to change its state of motion? That means the reluctance to change its state of motion is measured as its strength of interaction between the particle and Higgs boson. Okay? So you understand mass as this. What do you define as mass? Yes. What do you define as mass? If you think mass as kg, then what gives that kg that what is kg? What is 1 kg? This one or what gives that thing that feel? Yeah, if you think carefully, if you just go deeper and deeper and deeper. Albert Einstein went to talk about the fundamental nature of space and time. Boom, one whole thing came out of it.
Wait, so what is mass? Is it like amount of stuff, inertia, or is it like all the same?
Okay, when you talk about mass, there are two kinds of mass. It's like, what? This is getting messy. Messy, yeah. Yeah. Okay. There is a MI, inertial mass, and there's a gravitational mass. Very important difference. I'll explain to you why is it important. Why are we like out of space already? Okay, inertial mass is the reluctance of a body to change its state of motion, which is what Newton understood it to be. mg is gravitational mass. That's the mass that gives you F equals to mg, that mass. But can you see that fundamentally they are different? One doesn't need gravity to define. One requires gravity. It interacts with gravitational field. Now, why is it so important? Because Albert Einstein was thinking of this experiment. That if you are in outer space, by right you shouldn't have any gravitational field, right? If you're in deep space. But what he came up with was that if you have an acceleration of A up here, the person over here will say that I have weight. So the person inside will not be able to tell the difference between this acceleration and this acceleration. And if you read carefully, this is actually, if you read some book, this is called the equivalent principle. Now, why is it important? It means that if a person were to shoot a beam of light over here, and if he's in a craft that is accelerating, do you agree that the light beam will go like this to a person who is outside the craft? Yeah, right? So, light speed doesn't change, which means that to him, he sees the light beam as horizontal. So if he used the time it takes for the light to transverse one, he will measure a certain time. That this is 1 unit of time, right? 1 unit of time. But to a person who is outside, because speed of light doesn't change. So to the person outside, the light will take a longer time to bounce between the surface. So do you see that the person in the craft and the person out of the craft will register 2 different times? Exactly. Exactly. And if you go all the way back, right, it's back to this idea that you cannot tell the difference between this mass and this mass. The one that interacts with gravitational field that gives you the sensation of weight, and the other one that gives you the reluctance to change the state of motion, which is F equals to ma. So there are 2 different masses. And these 2 masses, mi over mg, has been determined to be 1.00007 zeros, 1, 2, 3, 4, 5, 6, something, that it is equal. Now, what's the consequence if it is not equal? Albert Einstein will be very unhappy. Yep. That means his theory is not complete. And at the extreme, certain neutron stars and the extremities of the galaxies and the universe, they actually discovered that Einstein's theory of relativity has flaws. Has flaws. yeah. At some extreme conditions, like in certain stellar conditions, black hole, neutron star, they found that the Einstein's theory of relativity doesn't seem to explain certain things. Yes. So it could be a chance for you to put your name there and come up with another M lah. Another M lah. Can? Okay, so have I answered your few questions? What all these messes and yeah. Not in IB, huh? Not in IB. Not in IB, So what is in IB? Okay, before I go on further, any remaining questions? But you see, this is the interesting thing about. I always believe that students should have the time to wonder. Einstein came up with all these things because they have time to wonder. I don't know. Sometimes is it wondering or is it daydreaming? Sometimes you can't tell the difference. Einstein was at the Switzerland as a pattern club. He was very xingnang, very free. So he thought of an experiment like when he was looking at the clock and then daydreaming. What if I move faster and faster and near the speed of light? Do I see the clock as going backwards or do I see the clock? How do I see the clock? Yeah, so he came up with this whole theory that when you move things and time dilates, length contracts, and all these things, because he has time to wonder.
How did he come up with like space-time and distortion of space-time?
A huge amount of mathematics. That one is a geometry kind of thing already. Yeah.
So in this situation, mass comes about as relative to motion.
Yes, but then that means that an object that doesn't move doesn't have mass, right? That's what your question is. So if an object doesn't move, now the question is, uncertainty principle also says that delta x, delta p bigger or equals to h bar upon 2. Now let me urge you to look, if you can see into the microscopic scale, into the atomic scale. The atomic world is actually a very dynamic environment. The phrase, the atom is at rest, doesn't have any meaning at all, because you never know whether it's at rest. So in the atomic world and the microscopic world, everything is jiggling around. Everything is jiggling around. So you cannot have something that is not moving. Even absolute zero doesn't exist in real world because of the uncertainty principle. There's always this fluctuation, there's always this jiggling due to quantum effects. So it will always be moving. So we always have mass. Sorry?
What does quantum effects mean?
Quantum effects. Quantum effects simply means one thing, that particle, if you want to, in the context that we're talking about, particles becomes wave. Yeah, it's one simple idea, but it leads to everything that we talk about. Why electrons have fixed energies inside the atom? Because electron behave as wave. If electron doesn't behave as wave, do you agree that the electron can take any orbit, any energy it wants? It can take any value it wants. But why is it that it exists energy state then? Because electrons behave as wave. And a wave trapped inside an atom needs to have can only take on specific number of shapes that exist. It cannot take on any shape it wants, which means that, say for example, this doesn't exist. If you have like this, it doesn't exist. It needs to be connected nicely back in the loop. So only certain wavelength exists, and therefore certain wavelength connects to certain momentum and therefore certain energies. That was the Bohr's model. Yeah, that was the first one. Now Bohr's model has its limitation because Bohr's model only talk about one electron, hydrogen, and one wave. Where you go to more waves, say helium and beyond, the waves of the electron starts interacting with each other. Therefore, this simple mechanics no longer work. But do you know that Bohr got the Nobel Prize because of this jump? He got the Nobel Prize because of this model. By treating particle as wave, he came up with a model which is based on this, and he correctly predicted all the energy levels in hydrogen. And because of that, he got the Nobel Prize. Even though his model doesn't work for everything else, only work for hydrogen. He got a Nobel Prize for it. Why? Because it's a big shift. It's a big shift. Yeah, it's a fundamental shift. Yes. Okay, yes. Yeah.
So I read something online. It's like I don't know, double slit experiment.
Oh yes, that is Tikababooms. That's Tikababooms. Okay, people, at the back of my mind, I know that I got syllabus to cover, but I thought these are really solid questions and excellent questions that I don't want to lose that opportunity. Okay, let me show you how wonderful the double slit experiment is. You start to wonder, you start to understand as I go through, it's like, what? It's like the implication of double slit experiment. Now, double slit experiment basically means that you got two slits, you send wave in, you got wave spreading, and then you got a pattern over here that is dark, bright, dark, bright, dark, bright. Yeah, this is wave interpretation of double slit. You send light waves through two holes, you see bright, dark, bright, dark, bright, dark, bright, dark, because of the interference. What is interesting is you send particles, electrons, one at a time, into these two slits, you will find bright, dark, bright, dark, bright, dark, bright, dark as well. Initially, it seems trivial. But other than, that means that wave exhibits this phenomena. So whatever that you send in over here also shows this phenomena. This must be a wave. You see the logic or not? If whatever you send here, and this is a wave, this forms a pattern, and only wave forms this kind of pattern, because it makes no sense for you to send two electrons and then it combines to become a bigger electron. Or two electrons not into each other and then disappear. It doesn't happen for particles, right? So particles don't show this kind of pattern. Only waves show that kind of pattern. So therefore, reverse deductions tells you that if you see this pattern, whatever you send in over here must be wave. But we are sending in electrons. So therefore, electrons are waves.
What's the thing about when you measure it?
This is what I'm going to go to now. Yeah, correct. If you put two detectors over here, do you agree that this pattern only forms when you have two things coming out over here interfering with each other? So by right, if you put two detectors over here, okay, if you put two detectors over here, let's call this position A, position B. Position B doesn't exist, we put the detectors in front. Do you agree that for you to have this pattern, you need to detect things coming through here at the same time, so that you got waves overlapping and then you can have the pattern? But they always detect only one. So for some reasons, the electron knows that you're spying on it, doesn't want you to know the secret. So it collapses into either this one or this one. But when you take this detector away, it shows phenomena that is only possible if it goes through both. You understand the dilemma here, no? The pattern can only be formed if things come through both at the same time. But when you detect it, it only exists at one or the other one. Now this is not the interesting bit. The interesting bit is when you go for position, you go to position B. You go to position B, do you agree that the electron have no choice now? It has already decided to exist at both. Agree or not? So by right, if you put at position B, it should detect at both positions already, because the electron has gone through already. No choice already, irreversible. But what is interesting is it also detects either this one or this one. Now what's the implication? The implication is that the electron passes through, then somehow saw that it is being spied on, doesn't like being spied on, it goes back in time and chooses either this one or this one. Which means that, what does this mean? It means that electrons exist somewhere here. When we say the electron is here or here or here or here, it's everywhere. It's everywhere. When you say that it has passed through, actually it hasn't. It has and it hasn't.
But then also it ends there at the same time on the screen.
Somehow it does. No one knows how. That's the interesting bit. That's the interesting bit about quantum physics. When you observe, it's a Schrödinger cat. The act of observing it changes the state of being observed. If you don't observe it, it shows certain things. If you observe it, it changes it. So you never.
It just doesn't change it, that somehow the electrons can form that.
If you can actually come up with a technique to observe without changing, this is groundbreaking. That's going to be groundbreaking. That's going to be groundbreaking. I can tell you. No one has done it before. No one has been able to do it since. Observing without affecting. It goes back to a TOK question. What do you do when you observe? I see you. I see you because light bounces off you and come to me, right? But in this world, it doesn't matter because you're much heavier than photons. Yeah, you don't feel like you're being hit by a lot of photons every second, right? But in electrons, the mass is 9.1 times 10 to the power minus 31 kg. You move near the speed of light already. So when you observe an electron, you're bouncing photons off the electron. It will change its state of motion already. So what you observe was its state. It is not, it is its state. It was the previous state. So the act of observing will change things in the quantum realm in a way that you don't know what was its real position or real momentum. So are you able to observe without affecting? No one has come up with a technique that is possible yet. Probably one of you. Probably one of you. Yeah?
I had a question, but it wasn't like quantum physics.
Okay, please go ahead.
It was like
Hang on, before this experiment is labeled as one of the most important experiments in the 20th century. This one, yeah. Yeah, it's one of the most. Young's, by the way, Young's modulus also came from the same guy. The Young's modulus, the rigidity of a material. The Young is the same Young. Yeah. Stress over strain, correct.
Anyway, back to like the guy in the box.
Equivalence principle.
So no, I'm not about
The guy in the box, yes.
It's just okay, like on Earth, right? Like a normal setting, and then you put like a guy in a box or a lift or whatever, and you drop that like off a cliff. So
yes.
Like free fall. Does that guy have weight?
The guy has weight. Okay, because weight is defined as the interaction between the gravitational field and the person. So m is not 0, g is not 0, so the person has weight. But the person feels weightless because n is the one that changed. The normal contact force is the one that changed. Okay. The reason why you feel gravitational force now is not because it's not because of the gravitational force. It's because of the normal contact force. Yeah, you feel weightless like the astronauts. Remember the case where you project something, and then that one. So actually, circular motion or orbital motion is free-falling motion. So the astronauts, it is wrong of us to say that astronauts are weightless. They feel weightless because they are free-falling. The normal contact force is 0. So you can feel heavier. In the reverse, you can feel heavier in a lift that's accelerating upwards because the normal contact force is bigger than the weight. Yeah, that's why fighter pilot, they can feel 9 Gs because the normal contact force is 9 times the gravitational force. Yeah, and when that happens, I don't know whether you're. There was an exhibition by NASA at Art Science Museum. Were you there? Okay, there was this G simulator. I don't know whether yeah, that goes around. It's that's the G lah. What happens is that when the pilots go through 9G, the blood starts to go down to the feet, and then they have technologies to help. So what happens is that the technology is that they have this suit that is a G suit. It compresses the thighs so that it forces the blood back up to the brain. Yeah. Yeah, it's not cool when you go through 9G. Yeah, not cool when you go through 9G. It basically, it's very uncomfortable. The G machine that you went through is only 1.5 to 1 G only. And you really feel, yeah. Dr. Andrew Yong and myself went through it. After I come out of it, it took me 15 minutes to recover. It was like, okay. Yeah, so coming back to the point, gravity. Let's take a macroscopic view. Gravity, what? Okay, Einstein's view of gravity is basically this thing where you put a material, you put a ball on the fabric, it basically stretches the space. Now, the interesting thing is that when you stretch space, you actually stretch time as well. So as you go into a region where there is actually, have you watched a movie called Interstellar?
Yeah.
Yes, a few hours on the planet, 27 years up there. Yeah. So it's not just an observational effect. It is real. It is real. The first observation that proves Einstein's theory of relativity, you know which experiment was it? There is not atomic clocks, there's this lifetime of muons. Muons. It's a particle. It's a particle. Yes, correct. So in laboratory experiment, the muons created in labs have a lifetime that is really, really short. So what happened is that muons are also created in the atmosphere, high up in the atmosphere. When a cosmic ray hits particle, it creates muon due to cosmic ray. You can go and read up. Cosmic rays creates muon. You can go and Google how it creates. But interaction with cosmic ray creates the muon. And due to the short lifetime of muon, none of them should be able to make it down to Earth. None. Zero. Because they will have decayed already. So the thing is that on Earth, we actually detect muons. We actually detect muons. If you have the chance to go to CERN, they have this activity where you build bubble chamber. But you build the cloud chamber. And you can actually see for yourself the amount of radiation we are constantly under. It's amazing amount of radiation. I was shocked when I see the amount of radiation we are under. Yes, and there's no radioactive sources, so it's actually just the environment. So these muons actually reaches Earth. What does this mean? It means that muons have a different lifetime? No, Einstein said no. This is actually a proof of my theory of relativity. Because when the muons move near the speed of light, 1 second to the muon is actually 2 hours to us. Yeah. So to the muon, it's only 2 nanoseconds. Yeah? But to us, it's 1.5 hours. So because of the difference in time, that's why muons can live all the way to Earth. So that was the first evidence that it is actually real. And if you think that this is some sci-fi thing, actually general relativity is actually used in GPS. Your phone, whenever you use a GPS, general relativity is responsible for it. Why? Because on Earth, you are here, the satellites are here. Yeah? Do you agree that gravitational field is different? And because of the difference in gravitational field, the time, 1 second here will be different from 1 second here. Do you know how GPS works? Do you know how GPS works or not? Whenever you use your iMap, you're using GPS, huh? Okay, how does it work? Come on, you should visit the How Does It Work website more often. So there are many satellites, GPS satellites that is hovering around the Earth. So when you receive a signal from this satellite, the satellite has an atomic clock over here. So it sends a signal that says when was it sent. And when you receive it, you have a timestamp as well. So knowing the difference in time, you'll be able to find the distance, correct? So in the computer, what it does is that it calculates the distance. So it knows that this is a satellite, and it knows that this is the distance from the satellite. So it will be able to detect that, it will be able to calculate that this receiver over here is able to calculate that you are definitely somewhere around here. Right? Now, you receive another signal from here. Then the same thing happens, you are either here now or here. Yeah, either here or here. Then you just need a third one to confirm whether you are here or here. So you just need at least 3 satellites. At least 3. The more you have, the more accurate it will become. Yeah? So let's come back to this. It goes back to time. Time. Yeah? If your time gets screwed up, everything gets screwed up. So it does get screwed up because at different distance above the Earth, the G is different. And when you take 3 times 10 to the power 8 multiplied by 1 nanosecond or 1 microsecond, you're off by 1 kilometer. Yeah, you're off by 1 kilometer. Just 1 microsecond off, you're off by 1 kilometer. In fact, 3 kilometers. Yeah, I think so. So the thing is, they have to take into account the difference in time because of general relativity. So that's every time you use your iMap, you need to really appreciate that relativity is actually taken into account. Not just some sci-fi interstellar movie kind of thing.
Wait, which one is general relativity and which one is special relativity?
Okay, special relativity deals with no acceleration, in simple words. General relativity deals with acceleration. Yeah, everything that has acceleration, everything that has gravity, that's where the general relativity comes about. And it's amazing that Albert Einstein, in that year when he came out with special relativity, which is 1900, go and find out, yeah? That year that he came out with the relativity paper, he came out with, I think, 4 papers that changes the world. I don't know how he can do that. One is on Brownian motion. You think Brownian motion is very simple? Brownian motion is not simple because he interpreted Brownian motion as the direct evidence for the existence for the atomic model. Yes, the model that thinks the whole world is made of atoms, this is a direct evidence because the jiggling motion is due to other invisible jiggly particles around. So that was one. Special relativity was one. There's another paper that sets the fundamental for lasers. That was another paper. The AB state and then yeah. So it was the fundamental for laser, which was invented 60 years later. Yeah, imagine you come up with a theory that people only know how to use 60 years later. Impressive, if you think about this. The fourth paper, I can't remember what it is. You go and find. There are 4 papers that he wrote in that year that shapes a lot of things that we talk about. And then 10 years later, that's when he came up with the general relativity. Yep. So
when do like gravitational waves like?
Oh, gravitational waves. Gravitational waves is basically the ripples of when two very massive objects orbits like this. Yeah, so it basically distorts. You can imagine that this fabric that is distorted over here. Where's the thing that I drew? Yeah, this thing over here. If you have something that goes round, basically the fabric of space-time gets distorted. Yeah, cannot take it anymore. Cannot take it anymore. So basically, the fabric starts to go in waves lah. And the LIGO experiment was actually designed to detect that, and LIGO detected that, and it was the LIGO team was given that Nobel Prize as well. I think they were given Nobel Prize for the detection of gravitational waves. Yeah, yeah, and only in very violent event like the orbiting of 2 black holes. And when they collide, you need massive mass, huge enough mass to create that effect. And you must understand how difficult it is. They're detecting things from millions of light years away. How do you isolate that from the vibrations of cars around? Yeah. So the whole experiment was actually levitated in air or levitated, so that it isolates the whole setup from the vibrations around. It's humongously difficult. The only one that in Singapore that is close to enough to it is that there's this lab in NTU where the whole lab is levitated in air. Oh. Yes. When they turn on the machine, the whole lab floats on a layer of air. Because the experiment that they do inside is so sensitive to vibration that they have to isolate everything else.
Last time,
Yeah.
me and Shani went to the entrance lab, they had like a superconducting thing, and it was like levitating.
Oh, that one is what do you call that? Meissner effect. Because of the superconductor, we'll talk more about this when we talk about EMI and stuff. Because in superconductor, when you put a magnet there, it has induced current, and the induced current will repel the thing up, and that's responsible for the floating. Yeah, it's because of that. But most of the time it's unstable, but superconductor is amazingly, it adapts to the thing that makes it stable, so it floats rather than bounce off. Yeah. Right, people, very enjoyable lesson with you. It started off of friction, then it's booms to like the universe, the outer edges of the universe.